you'll notice that it says Unit 4A. So Unit 4 is a really long unit, and so Miss Henry and I talked about it, and we decided to go ahead and break it up into the first half so that you can get a question before the end of the quarter. And then when we get to the second half of it, your test will be still over both parts of the unit. So your quest is over just this first half that we're doing, so we can get you one more grade in for the quarter. And then when we finish out the unit, the test will be over both parts, the first part and the second part. So just keep that in mind there. You'll see that we're going to be talking about integration. That is, our calculus is broken up basically into limits, derivatives, and integrals. So we've done limits and derivatives. We're now moving on to integrals, which means we're on the final third of our material. So today we're going to be doing the kind of the background behind integrals, where they came from, and that's called Riemann sums. Riemann was a nice mathematician back in the day. So we're going to look at that first today, and then I think next class we're going to start dealing with actual integrals. Right, so let's take a look at just right now as we talk about integrals and anti-differentiation. It's going to be very basic overall because we're not actually dealing with integrals yet. But just to give you kind of a general idea of what it is. So we were dealing with derivatives, and whenever we took the derivative of something, that was called differentiating it. So anti-differentiation is the opposite of that. It's basically going backwards. Kind of like squaring is the opposite of square rooting. Anti-differentiating, or taking the integral, is the opposite of differentiating. All right, so anti-differentiation, the opposite of taking a derivative. So you can kind of think of this as an inverse operation, like I was relating square roots and squares there. So if we're given a derivative, or even just a function, when we anti-differentiate, we're going to find the previous equation that, should we take the derivative of it, would give us our original equation there. So when you're given a derivative, when you anti-differentiate it, you find the previous, or the original function. You find the previous, the original function. So you're basically going back a step. For example, if I gave you your velocity function, you can anti-differentiate it and find your position function. All right, now your integral is the operation used for anti-differentiation. Operation used to anti-differentiate. And you'll see the word integrate. You integrate a function, which is the same thing as anti-differentiating. This operation looks like a really elongated S. Now, it's an operation similar to how square root is an operation. For differentiating for derivatives, we use d dx, or the prime notation. So this is used to indicate that we're going to integrate something, take the integral of it. So you'll see it's written as this elongated S of some function. And sometimes it will give you bounds. It'll ask you to integrate specifically from 1 to 8 or -1 to 9. If they give you bounds, we write the lower bound down here, the upper bound at the top. And we have to specify what variable we're integrating to. Just like we took our derivative with respect to a variable, like we would say d dx, we would take the derivative with respect to x. We integrate with respect to a certain variable. And again, oftentimes it is dx. So this is common notation for an integral. And just kind of off to the side, a and b are your bounds. And dx means with respect to x. This is for what we call a definite integral, meaning there is a defined amount. An indefinite integral does not have bounds, so it would look the same, but without your bounds A and B. So derivative was finding the slope at any given point in time. So taking the derivative allowed us to find our slope. Well, integration is used to find the area under the curve. So what is integration used for? It is used to find the area under the curve. Find the area under a curve. Okay, so if we were to graph a function and I asked you to integrate from 1 to 2, take your function, shade underneath it between 1 and 2, find that area, and that's exactly what the integral does. So let's go ahead and take a look at that first graph on your view. So here we have a nice picture of y to the x, or sorry, y equals x squared. It's our parabola. Now we've isolated it just from 0 to 2. And again, you'll notice we shaded underneath our curve. This is my x squared curve here. Shading underneath it, if I were to integrate this from 0 to 2, this would allow me to find what the area of this shaded region is. Okay, so that's again what integrating is. Now, we could actually approximate it using just basic geometry. Geometry you learned back in elementary school, and that's what we'll be doing today, called Riemann sums. And then we'll learn how to actually find the exact area. So if we take a look at this picture here, you see it poses the question, how do we find the area under this curve? Well, we've got some options, right? We could try to do a triangle. That could give us a pretty good estimation there, specifically for this one. But if I change this to sine squared of x, perhaps a triangle wouldn't be best there. We could try rectangles, right? If you see actually at the bottom of your page, the first one says, let's estimate using the area of a rectangle. So here is my curve, and a really rough estimation, probably not a very good one, would be if I just took the area of this rectangle. Going from 0 to 2, so I know that my width here would be 2, and my height ends up being actually the height of your function at 2, so your height here would actually be f of 2, or f of x in general. Now, f of 2 at this point would be 4, and so if I were to find the area of my rectangle, what would be the area of this rectangle? 8. But as we can see, there is a large space of this rectangle that's not actually part of my curve, so 8 would not be a very good estimation. But let's suppose that we did 2 separate rectangles. Go and flip your paper over in your notes. Our previous one was in a big time overestimation, way more than we needed. Now, would you agree that doing 2 separate rectangles is a bit better of an estimation? So I start off with just 1 rectangle, really not a good estimation. If I break it up into 2 rectangles, then I have a little bit better. There's less white space that we would have to make here. Okay, so if we were to find the area using these 2 rectangles, then I would have to do the area of this rectangle plus the area of this rectangle to find our new approximation. Now again, this is going to be closer to the actual area, but still it is a pretty big overestimation. So this is better, but still an overestimation. Still an overestimation. Okay, so what if we decided to go with even more rectangles? Looking further down your page. Okay, so say that we had 4 rectangles. Now my rectangle widths are even smaller, it's only a half, but you'll notice there's even less white space that's that we would want to omit. So again, we would have to find the area of each individual rectangle, add it together, and we would get our overall approximation. Even better, but still an overestimation. And the reason why we still have an overestimation is because my rectangles end up going outside of my curve. It goes above it there. Okay? Now, we could pretty easily find this area. You know how to find the area of a rectangle, and I'm sure you can do it 4 times, and I believe you can even add those numbers together. And as we see, the more we have, the larger number of rectangles we have, the closer to the approximation we get. Alright, now we've been drawing rectangles. This back down. For all these examples so far, our rectangles have been where it goes outside of the curve, and if you notice, the right-hand corner is what lies on my curve. This is actually what we call a right-hand estimation, dealing with right-hand rectangles. What if I were to draw it the other way? If I were to take this exact same curve and instead draw it where my left corner is on the curve, then I would have something like this. And I think there might be a little bit there. Now, as you can see here, still not a super good estimation. Again, having 4 rectangles compared to our 1 is going to be a better estimation. But whereas before we were overestimating, now we are actually underestimating. Right? So this is what we would call a left-hand sum, using left-handed rectangles, where the corner on the left side is what lies on my curve. Now, using a left-hand approximation and right-hand approximation, we can get good general ideas. Again, the larger number of rectangles you have, the more accurate it's going to be. And if we wanted to go back into a realm of limits, if we did the limit as the number of intervals approaches infinity, that would actually give us our most accurate approximation. Because if we had infinite, even though we can't obtain infinite rectangles, then that would minimize how much white space we have. And we'll probably deal with later the definition of a limit in terms, the definition of integrals in terms of limits. Okay, so we've dealt with left hand, and now we're looking at, I think, the bottom of your page. Bottom of our page here, it's kind of hard to see, so you might want to outline a little bit, is where we have that left hand, or that left-hand rectangle, where the left corner lies on your curve. And again, as we can see, this is going to end up being an underestimation. Okay, so it does change your estimation. Now it's going to be less. But it's still, again, the higher the number of rectangles, the better approximation. And as we were saying, how many rectangles do we need to make in order to get an accurate estimation? Really, infinite rectangles will give us the most accurate. Okay, now as you notice, we've been dealing with an increasing function here. So since my function was increasing, when I did the left-hand rectangles, it ended up being an underestimation. When I did the right-hand rectangles, it ended up being an overestimation. It really depends on whether your function is increasing or decreasing to know if it's going to be over or under. And that is a type of question that the AP exam likes to ask, is if your estimation would be over or under the actual amount. So you have to keep that in mind. So here, I believe it's on the top of your next page, is an example of your right-hand estimation and your left-hand estimation. Notice that for your right-hand estimation, you start on the right when you're drawing your rectangles, and you'll notice it's the right corner that lies on your integral. For a left-hand estimation, same idea, but you start on the left as you draw your rectangles. And as you can see, it's the left-hand corner that lies on your integral. Now, we would call these here inscribed rectangles for this particular example. And we would call these ones circumscribed rectangles. And again, this is just specifically for this example. If my function would have changed to be a decreasing function, it would result in different things. So our inscribed rectangles, you may remember this from geometry. This means that they are inside the curve. They fall completely underneath the curve. Circumscribed, they go outside of the curve. Part of it falls above the curve. Now, something interesting with this, I'm going to go back to this here. So we see we have right hand and we have left hand. Would you agree with me that if I were to actually go for the midpoint in between, let's change this color. If I were to go halfway here, let's see, halfway here. Would you agree that this is kind of a nice compromise? Gets a little even more accurate. So we have right hand, we have left hand. Even more accurate is our midpoint. And then another method that we use is actually called a trapezoidal sum, where we use trapezoids. Those are a little bit harder to draw, but bear with me as I try to draw that over here. You're used to probably in geometry, your trapezoid would look something like this, or the more common one, you think of an isosceles trapezoid, where our bases are the parallel lines. Think of that trapezoid turned sideways. So if I think of this as my parallel line, set of parallel lines, my bases, and then this as my trapezoid. And then same idea here. And same idea here. Still not exact, but a whole lot closer than either of my previous estimations. So what we're going to be doing today is figuring out how to do each of these estimations. Right hand, left hand, midpoint, and trapezoidal. Really, it's not bad, it's just a lot of algebra involved. Alright, so let's take a look at the bottom part of that page there, filling out this chart. So this is just talking about what it would look like with an increasing function as opposed to a decreasing function, what's an overestimation, what's an underestimation. So we'll just draw a rough increasing sketch, kind of like what we have above, and a rough decreasing sketch. Right. Go ahead and replicate that for each of your boxes. You're going to get an idea of what's over and what's under. Alright, so for my increasing function, if I start with my rectangles to the right, where again that right corner is on the curve, we see this is an overestimation as we don't look above. But if I look at my decreasing curve and do rectangles start on the right here, notice that all my rectangles are underneath the curve, and thus we have an underestimation. Alright, so then taking a look at my increasing curve again, if I did my left-hand Riemann sum, my left-hand rectangles, starting with the left side, creating my rectangles. Here I have this as an underestimation, and you can probably guess what it's going to be for you. I draw my left-hand rectangles. This is an overestimation. So a little bit of this is going to be exercising your brains of going back to pre-calc and algebra 2 and remembering what that parent function looks like, what transformations have happened, and are you dealing with an increasing or a decreasing function. All right, any questions over this basic idea before we actually dive into it? Okay. I'm going to flip that page over and let's take a look at kind of the general setup of it. Alright, so again, that big idea is that we break it up into rectangles or trapezoids, depending on which rule, and we're adding all of them together. You'll see this notation. Well, actually, it's down here. Anybody remember what this thing's called? Yeah, it's sigma. It's a summation notation. It means we're going to add things together. So sometimes you'll see this notation indicating that sum. What we're doing today is called Riemann sums. Riemann sums, and again, this is approximating that area under that curve. And again, Riemann was a mathematician. I was reading a little bit about him in one of the calc textbooks. And it sounds like he was a pretty smart guy, contributed a lot to, a little bit to calculus, but also a lot to complex analysis, I think number theory, and geometry. But the poor guy died at the age of 39 from tuberculosis. But think of how much he accomplished before he even turned 39. Pretty young. Alright, so our buddy Riemann here was kind of the big guy for coming up with this idea here. And again, we're just approximate all those values together. So we're adding all these rectangles or trapezoids together. Now we've got two scenarios. We can have where our rectangles are broken up into equal widths, or as you see down further your page, unequal widths. I think more common is typically the equal one, but you're just going to read the problem. It'll say 4 equal intervals, or it'll give you the different intervals if they're not equal. Now, let me go ahead and redraw that picture over here off to the side. I'm going to keep going back to this original picture that we were dealing with of x squared. Alright, so as we broke this up into rectangles, regardless of what rectangle we use, left, right, or midpoint, notice that we had a width of my rectangle. My rectangle, the area of a rectangle, is length times width. So if we think of this width here, this is simply the difference of two x values, right? Now, if I wanted to get equal widths within here for equal intervals, would you agree that I take my starting x value, my ending x value, subtract them, and divide by however many intervals I want? That'll give me those equal widths there. If I wanted 4 equal ones, take this minus the beginning and divide by 4. So that's what this formula is here. That delta x, which is that change in x, this is simply your width of that rectangle. And it's your end point, your upper bound minus your lower bound, your starting point, divided by however many intervals we have. So n is the number of intervals. And again, the problem will communicate that to you in one way or another. Alright. So for this specific problem here, we have that it's going from 0 to 3. And for this one, I'm going to tell you we're aiming for 3 intervals. So if I were to do my delta x for this problem, 3 is my ending x value, 0 is my starting x value, and I want 3 intervals, so that would mean that each interval is a width of 1. It's usually good to draw a rough sketch of what your picture is going to look like. Even if you don't know what your function is, go ahead and at least draw the number line so that you can label the different intervals that you have. It makes it a little bit easier for calculating your approximation. Alright, so we're going to go, we're starting at 0. We have 1, 2, and 3. Now there was really no information given to me at all whatsoever about this function. It says f of 0, f of 1, f of 2, and f of 3, but I don't know if this is increasing or decreasing. That's fine. It's not going to make too much of a difference for us in setting up our left-right Riemann sums. Alright, so actually to do this, it would probably be good if you had some different colors. So if you have colored pencils, or if you have some pens or eraser or something, you can use those if you would like. I have colored pencils up here. You can go ahead and come up and get some colors. You're probably going to want about 3 different colors. Okay, so again, we don't really know what this graph looks like, but we're just going to go ahead and draw in our rectangles just to help us out as we come up with our formula. So we have 3 different rectangles, so let's just go ahead and draw in our 3 different rectangles. Again, we don't know the heights of these, that's fine. We're just going to give us a nice picture to follow here. I should use my crayon feature. Crayon or however you guys say it. It's like I'm in kindergarten. Okay, just because this is relaxing. Like you're in kindergarten doing calculus. Alright, so first to calculate our left Riemann sum. Key thing, left. So it means we're going to start from the left. So I need to find the area of each of my rectangles. And again, we're starting with that left side. So looking at my picture over here, what I would have is this little interval. And that's at 0, 1, 2, 3. So if I was concentrating on my figure here, just going from 0 to 3, this is what I'm looking at. My rectangle is created by starting on the left-hand side. Right, so for each of my rectangles, it's going to be width times the height, width times the height, width times the height. Now my width is that delta x. That's what determined how far apart we're going. So my left Riemann sum is going to be delta x. Oops. Delta x times the height. And the height is going to be f of 0, right? 0 was my starting point, so f is 0. I'm starting on the left-hand side here. That's what allowed me to draw my rectangle. Okay, so that is the area of my first left rectangle. Now let's do that for my middle rectangle. Again, looking at my picture over here, what determines my height? The left endpoint there determined my height. So f of 1 is what determined my height. Again, here, I go to the next interval, it's the left side that determined my height. So again, delta x, that's my width here, times the height, which would be f of 1. And then for my last rectangle, again, delta x, because again, this is delta x, times f of 2. So again, you're starting with the left side. What you notice is that with your left Riemann sum, you use all the intervals except the very end one. With your Riemann sum, with the right one, you'll notice it goes to the end one. Right, now our delta x for this ended up being 1. We're going to leave it like this for now because it's just kind of a general scenario for what we do. Alright, so now my right Riemann sum. If I were to draw my right Riemann sum over here. So 1, 2, 3. So right Riemann sum, I use that right-hand side. That's my starting point for my rectangle. We're still going to go and just use that picture there. I'm going to do this up here for you. I use the right-hand side to determine my height. And again here, I use the right-hand side to determine my height. Okay? So you notice now that it is f of 3 that was my height here. F of 2 was my height for this, and f of 1 was my height for that. So really we're just starting on the right side. Now again, for the Riemann sums, we're dealing with rectangles here. So my width is still delta x, but now my height, starting from the right side, would be f of 3. So that's my blue rectangle. Now for my next rectangle, the green one, delta x times, instead of f of 1 being my height, f of 2 is now my height. So again, starting on the right side. And then last I have delta x, this is my red rectangle, times f of 1. So again, you'll notice it's the rightmost. Okay. Now, I went from right to left when I was writing my Riemann sum here. You could, of course, said delta x times f of 1 plus delta x times f of 2 plus delta x times f of 3. Just for visual sake, I went from right to left. Now, my midpoint sum. Midpoint means we're going to have to find that value in between. Now, a note to, an important thing here is that midpoint sums can only be used when we have equal widths. I mean, I guess they could ask you to do it with unequal widths, but it's most likely going to be used when we have equal width intervals here. Alright, so the thing is they did not give us our midpoint, so we can figure it out. What's going to be the midpoint between 0 and 1? 1/2. How about between 1 and 2? 1.5, or you could say 3/2. What about 2 and 3? 2.5. Good. So that is going to be the height that is used. If I were to draw that on here, I would go halfway, halfway, and again halfway. Okay, so that's the idea that we have here. Still, your width is the same delta x, but now your height is determined by the midpoint rather than either of the endpoints of your rectangle. Alright, so for that red rectangle, again, delta x times now f of 1/2, or 0.5. My green rectangle, delta x times f of 1.5, or 3/2. And then my blue rectangle, again, delta x times f of 2.5, or 5/2. Most likely that's going to be your better approximation of those three. Alright, so now our trapezoidal sum. If you do not remember your area formula for a trapezoid, make sure you write this somewhere within your notes. Alright, so for a trapezoid, we're going to be looking at a trapezoid that looks like this, as we're going to be using the x-axis as our base, and the sides of the rectangles are sides of the trapezoid. So for a trapezoid, these are our bases, and the height is actually the distance between your two bases. So you're used to thinking of it this way, we're going to be turning it on its side. So your area for a trapezoid, does anybody remember what it is? You're very close. You're very close, yeah. It's 1/2 times h times base 1 plus base 2. Or in other words, h times base 1 plus base 2 over 2. Very good. So it's 1/2 the height times the sum of your bases there. Okay. So what we need to take a look at then is, so this ends up being a lot longer of a form. It's still not bad, it's just a lot to keep track of. So if I were to do a trapezoid with this red piece here. Alright. So this is going to be 1/2 times my height, which is delta x, times base 1 plus base 2. Base 1 is the left height, base 2 is the right height. So f of 0 is the left height, plus f of 1 is the right height. Okay, so that was the area for the trapezoid of just this interval. Now we have to do it again for the green one. So So 1/2 delta x times f of 1 plus f of 2. Okay, so that is if I were to do a trapezoid on the second. And then my last one, again, 1/2 times delta x. I can squeeze it in here. F of 2 plus f of 3. And again, what my trapezoid looks like on this would be taking that left and right endpoint and making a trapezoid out of it. Your trapezoidal sum is always going to be the best approximation of these formulas. All right, now notice that with our midpoint sum here, well, actually for each of these, they each had delta x in common. So we could have rewritten this as delta x times the quantity f of 0 plus f of 1 plus f of 2. And we could have done the same thing to my right Riemann sum, and we could have done the same thing to my midpoint sum. Now, if we look at our trapezoidal sum, notice that each of these, so this is my first rectangle, my second rectangle, and these are trapezoids, my third trapezoid. They each have 1/2 delta x in common. So we could actually take out of this, factor out 1/2 times delta x. And then let's take a look at what we have left inside. Alright, so I have f of 0. How many f of 1s do I have within my entire thing? Yeah, 2 of them. Which makes sense because it is shared by both trapezoids there. Okay? Now I have, so I've taken care of this one. How many f of 2s do I have? Yeah, I also have 2 f of 2s. Because again, that is also shared by both the green and blue trapezoid. And then finally I have f of 3. Now if you happen to remember this pattern, that can save you a little bit of time. You can, you don't have to remember this pattern, you can substitute in your values from up here and simplify, that's fine. But that can take a bit of time. So it's your 1/2 times the width, and then it's your left endpoint, your right endpoint, and twice of every one of these. Okay, questions on that? Right. Let's do some actual problems with actual numbers. Oh no, we have unequal ones. Okay, so that was our equal. We'll go a little bit quicker through our unequal ones. Alright, so we'll notice here we have from 0 to 1, 1 to 5, and 5 to 7. If I look in between, this distance here is 1, this is a distance of 4, and this is a distance of 2. Not the same width in our rectangles. Alright, so again, step 1, you've got to find your individual delta x. Because each interval is going to have a different one. And the individual delta x's. So we're going from 0 to 1. My delta x here is 1. So with the from 1 to 5, my delta x is going to be 4. And from 5 to 7, my delta x is 2. Okay, let's go ahead and draw our number line to give us an idea of what we're working with here. So I have 0, 1, 2, 3, 4, 5, 6, 7. Cool. Alright, and my rectangles here. So we have 0 to 1. We have 1 to 5. We have 5 to 7. Riemann sum. Again, starting with your left endpoint. So my delta x for this first rectangle is 1 times the height, so based upon the left side would be f of 0. That's my right rectangle. Yes? We don't know for this problem what it is, so it doesn't matter for us. Increasing, decreasing comes into play to decide if it's an over or underestimation. So you would have to be given more information for them to be allowed to ask you that. Your question. Okay, so then my green rectangle now. This board is very sensitive lately. The new year, I don't know. Alright, so my green rectangle, what is the width here? 4. And my height of the green rectangle on the left Riemann sum is going to be f of 1. And then my width of my blue rectangle here is 2. And the height of my rectangle based upon the left Riemann sum is f of 5. Alright, any questions on that? I want you guys to go ahead and do the right Riemann sum and the trapezoidal sum for this. Let's see what you get. Okay, again, remember with your right Riemann sum, just make sure you use the right-hand side when you write your intervals. It doesn't matter if you go from 0 to 7 or 7 to 0. Alright, so our right Riemann sum, we should have gotten 1 times f of 1 plus 4 times f of 5 plus 2 times f of 7. And again, you could have done 2 times f of 7 plus 4 times f of 5 plus 1 times f of 1. It's your cumulative property for the round since it's a addition. Are we good with that? Okay. Now your trapezoidal sum. Say you didn't remember the condensed down formula. 1/2 times my width here, which is 1, times f of 0 plus f of 1. Actually, if we look with our unequal widths, we can't condense it down, because the reason why we were able to condense down our last one is because they all had not just 1/2 in common, but they had the delta x in common. It was the same width every single time. So you could pull out that 1/2, but it's not the same width for every interval, so you couldn't condense it down to this nice formula here. Alright, and then we would have gotten, so that was my first trapezoid. So plus 1/2 times 4 times the sum of f of 1 plus f of 5 plus 1/2 times 2 times the sum of f of 5 plus f of 7. Do we agree with that? I didn't make any mistakes there. Okay. Questions on that? Again, same idea. Just they would give you the different interval widths. Yes, Mark?
Could you ask us for that? It wants to simplify it down.
On free response, you don't have to simplify down. What you'll see today is that we do actually have to find the f of 7 value, f of 5 value. But you don't have to simplify it down completely. Of course, multiple choice, always be ready to. In fact, your homework for tonight, guys, the answers are simplified down completely, so I would recommend pick maybe 2 or 3 problems to simplify completely, because as we know, it's not always the calculus we struggle with, it's that arithmetic that we struggle with. So on free response, you're able to, after you've found f of 7, f of 5, substitute in those values. You don't have to simplify completely, but I would recommend for your homework, pick a few and simplify completely just to practice your fraction ability using multiplication rules. Alright. Finally, number 1. Alright, it says let y equal 2 minus x squared on the interval 0 to 2. And let the interval be divided into 4 equal subintervals. Find the value of the Riemann sum. And this is just the notation there for Riemann sum. This is the summation from 1 to n of f of x sub I times delta x using left-hand endpoints. So you're going to see a lot of different ways in which they will represent a Riemann sum. This is one of those ways. Okay, so that means that Riemann sum. Notice here they have specified whether they wanted you to use the left or whether they wanted you to use left hand, right hand, midpoint, or trapezoid. Okay, so they've given us our function here. They've given us the interval. This is my a value and my b value. And they said in 4 equal subintervals. Notice it's equal, so this means we're going to have 4 different intervals my n value is. 4 rectangles we're dealing with. And again, we are working with the left-handed endpoints. Okay, since this is equal intervals, let's go ahead and let's draw out our number line of sorts. And we know we're going from 0 to 2, but we need to know what each of those intervals are, so we need to find our delta x. Remember, delta x is b minus a over a. So for this particular problem, 2 minus 0 over 4, which gives us what's that? Okay. So we're starting at 0. So we have intervals of 1/2. So I think this would be 1/2. This would be 1. 1.5 or 3/2. So we're going from 0 to 2. We've got 4 different subintervals here, thus 4 different rectangles. Now, if you want, it can be helpful to go ahead and think of what that curve looks like. Or you can think about that at the end. Let's go ahead and talk about it now. What type of graph is this? What does this look like? It's a parabola. Good. What's happened with this parabola? Good. It's been flipped upside down. So if we were to do a rough sketch of it, let's see, it's got a y-intercept of 2. It would look something like that, right? Now we are specifically interested from 0 to 2, so we're looking, would you agree that this is increasing or decreasing on that interval? Decreasing, right? So again, you don't have to necessarily draw this, but it's good to have that kind of general idea of the sketch. So I'm just going to go and draw something or other. I don't know exactly, but that's just going to help me out with drawing my Riemann sums and approximating that there. Alright, so left-hand Riemann sums. That means I start off with f of 0 over, and oh, that's good. It's a crooked rectangle there. Okay, so there's my first rectangle. So f of 0, notice, was my left point. Okay, so then next, my left corner is on the curve. My left corner is on the curve. And my left corner is on the curve. Now again, you don't actually have to draw that sketch of the graph. That's just kind of to help you out visually. Just like we did before on the previous page, we didn't know what the graph looked like. We just drew rectangles to help us out. You can do that as well. All right, so we want our Riemann sum using left-hand endpoints. All right, so my left-handed Riemann sum. I'm going to use the summation notation. Okay. My delta x times my height. So I have it's delta x times my height, which would be f of 0, plus delta x. Do you guys agree we can take out that delta x and rewrite it? Let's do that. Make our lives a little bit easier. Alright. So f of 0 was my first one. F of 1/2 is my next one. Then f of 1. Then f of 3/2. Be careful not to get too carried away. We should have in here 4 different rectangles. One of the biggest mistakes is that you guys get carried away and go throw on an f of 2. We have 4 different rectangles here. Alright, let's go ahead and actually substitute in these values. What was delta x? 1/2. Okay, now we can actually find f of 0. They gave us that function was 2 minus x squared. Okay, now again, for response, you don't have to simplify it completely. So you could go ahead and leave it as 2 minus 0 squared. And I trust that you can handle that 0 squared is 0 and 2 minus 0 is 2. Alright. Now f of 1/2, we're probably getting some fractions. I'd say let's go ahead and leave that alone. So that'd be 2 minus 1/2 squared. That's my f of 1/2 value. Okay, now f of 1. 2 minus 1 squared. And 3/2. 2 minus 3/2 squared. Okay. For response, at this point, you can leave it alone. You're done. Make sure you do actually substitute in your y values, your function values. Questions on that? Okay, so that was my left-hand side. Now, if I were to ask you if this was an overestimation or an underestimation, what would you say? Yeah, this is an overestimation. Notice we had a decreasing function with the left-hand interval, so this ends up being an overestimation. Alright, next up we have let y equal x cubed under interval 0 to 4. Let the interval be divided into 4 equal subintervals. Find the value of the Riemann sum using right-handed endpoints. Alright, so again we have 4 equal subintervals, so n is 4. This is my a value, this is my b value. This is again just that notation for Riemann sum, but notice that now we are using right-handed endpoints. I believe you guys can handle this. I'm going to let you go and do this one completely on your own. So with this one, we have our function is x cubed. We know that on the interval from 0 to 4, that's going to be an increasing function. Again, you can draw that. You don't have to, though. We've got 4 equal subintervals from 0 to 4, so we find that our delta x, our width of each rectangle, is simply 1. So we have from 0 to 1, 1 to 2, 2 to 3, 3 to 4. And right-hand Riemann sum, so we are starting off, we're going on the right side. So we have f of 1 determines the height, f of 2, f of 3, and f of 4. Alright, so again, it's the width delta x. I guess I'll put in here delta x. Times each of those function values. Now again, we have to go back up to our actual function and put in our actual values here. So delta x here is just 1. You don't really have to write that in, but that's alright. Alright, so f of 4, our function is y equals x cubed, so that would be 4 cubed plus 3 cubed plus 2 cubed plus 1 cubed. Again, you could leave it right there or simplify from there. Questions on that? Okay, show me thumbs up, thumbs middle, thumbs down, how you feel so far with this. Wonderful. Okay, let's take a look at our midpoint one. I like this one. Okay, so we have let y equal the square root of x. That's our new function. And we have an idea, a general idea of what that looks like. But notice it's on the interval 1 to 9. And it says let it be divided into 4 equal subintervals. So again, n is 4. And here we're going to be using midpoints. Again, that's just notation for Riemann sum. So notice that we're not starting at 0. In fact, we're starting at 1 instead. So this is going to give us some lovely fractions. Make sure you're always aware of your interval. I know my square root curve looks something like this. Now, I'm interested only from 1 to 9. But let's go and figure out what our subintervals are going to be here. So delta x is 9 minus 1. So this is A, this is B. 9 minus 1 divided by 4. What would that give you? 2. I guess it's not actually that. Maybe it's later we'll do the fractions. Okay, so we're starting with 1. So we're actually not really interested in what's going on over here. I think I would probably leave that in regardless. But we're not interested in what's happening there. Okay, so 1. So 2 later would be 3. 2 later from there would be 5. 7. 9. Okay. Now we're going to be using the midpoints. So we probably want to know what our midpoints actually are. What is the midpoint between 1 and 3? 2. Okay. Halfway between 3 and 5 is conveniently 4. It's really not that bad. Okay, and then we have 6 is in between, and 8 is in between. This determines our height. Alright, so our midpoint Riemann sum. My width now is 2. And now my function height is based upon that midpoint. So it would be f of 2, f of 4, f of 6, and f of 8. As for your midpoint, you will never use your endpoints here. Alright, do we agree so far? Okay.
So we have to use the notation, like write the
It's probably good to do. I mean, you can write out Riemann sum, but it's good to specify that you're finding the Riemann sum and which method you're using. Yeah. I'll look to see if there's any particular like shorthand notation for it or something. All right. I guess technically this is delta x, but that's all right. We know it's 2. All right. F of 2. We're dealing with square roots, so that's just square root of 2 plus square root of 4. I trust you know that's 2. Square root of 6 and square root of 8, which you could simplify as well. Otherwise, here you go. Great. Questions on that? Okay. Now let's take a look at our next one. Trapezoidal. So here we have x squared minus 1. And this is on the interval -2 to -1. Let the interval be divided into 4 equal subintervals. That doesn't look terrible. But when we look at our a and b value, we notice that that's the entire interval is only a width of 1. So when we look for our delta x, we see it's going to be not so fun. Alright, let's go find our delta x first. So b minus a, -1 minus a -2, over 4 intervals. What does that give us? 1/4. Okay. Now, let's think of what our curve is here. This is a parabola facing upward, right? I'm just going to do a rough sketch here, and it's wider than so something like this. Now, we're interested from -2 to -1, so would you agree this is a decreasing function at that on the interval? Alright, so I'm going to draw something like that. So we have -2 to -1, and it is delta x of 1/4. So what would be my next interval mark? If it's 1/4 in length, it starts off at -2. What's my next mark? Yeah, -1 3/4, -1.75. Or we can think of it as -7/4. You can use either way to mark it up. Because when we think of it, 2 is the same thing as -8/4. So subtracting 1/4 from there, or adding 1/4 to that would give you some -7/4. Alright, what's my next interval? Good, -6/4 or -3/2. Or again, -1.5. And then I would have -1.25. And finally my -1. Here are those fractions I was looking for. Here, I should be consistent. Alright, we know this is going to be a decreasing one. And we're dealing with trapezoids. Alright. Okay. So we have our trapezoidal Riemann sum. I forewarn you, this is going to be a long one. Okay. So our trapezoid formula, 1/2 times the height, the width of your trapezoid here, which is 1/4. And then go ahead and list out everything else. See how far you can get with it. You can use the condensed formula or the non-condensed one. Let's see what you got. Alright, regardless of whether you did condensed or not, you should have gotten something along these lines. This is our first trapezoid, -2 and to -7/4. Then our next trapezoid, -7/4 to 3/2. Next one, -3/2, -5/4. And our last one, -5/4 to -1. Condensed formula, we've got 1/2 times 1/4. Okay, but we've got our endpoints here. and then twice of everything. Do we agree with that? Yes? Okay. So now we have to actually use the equation they gave us and find those f values. So x squared minus 1. And yes, we have fractions, but fortunately this is a free response. We don't have to sense that. Alright, so we've got 1/8. And again, our function is x squared minus 1. Alright, so -2 squared minus 1 plus 2 times. Be very careful with your use of parentheses. Make sure you use them in the proper places. Alright, so x squared, y equals x squared minus 1. Okay, so -7/4 squared minus 1. 2 times that. Plus 2 times -3/2 squared minus 1. Plus 2 times -5/4 squared minus 1. Plus -1 squared minus 1. Let's just double check. That. Okay, I think that's it. Questions on that one? It's really not that bad. Just keeping it all straight and everything's good. I feel like trapezoidal is the one most commonly where you leave out a piece here or there. So just do a real quick double check to make sure you got it. Okay. Let's take a look at our last ones. So number 5 here says the function f is continuous on our closed interval 0 to 60 and has values that are given in the table. Using 5 subintervals of equal length, find the left-hand approximation, right-hand approximation, and midpoint approximation. This really isn't bad, and what's nice is they've actually given you these values. Now it says that we want 5 subintervals of equal length. So this means n is 5. So if I were to go ahead and do my delta x here, it'd be 60 minus 0 divided by 5, which gives me intervals of what? 12. Okay. So you can go ahead and draw out your number line, but they already gave us the numbers here, right? So I'm going to go ahead and use this. So we go from 0 to 12, 12, 24, 36, 48, 60. 1, 2, 3, 4, 5. All right. So part A, left-hand approximation. All right, so my left-hand Riemann sum. Again, we're starting with the left side. So the width is 12 times the left-hand side, so f of 0. My next one would be f of 12. The next one is f of 24. The next one is f of 36. F of 48. And do I include the f of 60? No. We're doing left hand. We've already got 1, 2, 3, 4, 5 intervals. Okay. Again, if you want to draw those rectangles, okay. But we actually know these values. So f of 0 is just 0. F of 12 is 10. F of 24 is 13. F of 36 is 15. F of 48 is 13. There we go. Alright, I want you to go ahead and try B and C. C makes you do a little bit more work. So you've got your right-hand Riemann, the midpoint, and again, that midpoint we had to find out that value in between, but they gave that to us on our table. Okay, so now let's take a look at that final last one. Trapezoidal approximation. Same idea. They gave us the chart with the values, but something you have to be very careful with here is as you read the problem, it says it's continuous on the closed interval 2 to 9 and has values that are given in the table. Find the trapezoidal approximation for this. So what this is saying is the integral from 2 to 8 of our function. And again, we can use trapezoids to help us approximate that value. So even though the interval they gave us was 2 to 9, that was just simply telling us that it's continuous on the interval. What are we interested in approximating? 2 to 8. So you've got to be really careful to look at your bounds here. This is to tell me that it was continuous on the interval, but this is what we're actually trying to find. So when we go to, so what we have is that we're only interested from here to here. We actually don't care about that guy at all whatsoever. Alright, so just be careful with that. They'll try to trip you up with that. Alright, so we're approximating this with trapezoids. Now let's see. They didn't tell us if it's a certain number of intervals. They didn't tell us the width of it. But we're just going to use the intervals that are given to us here. So if we go ahead and draw our chart, we have 2, 3, 4, 5, 6, 7, 8. 3, 6, and 8. So my rectangles here are from 2 to 3, 3 to 6, and 6 to 8. Okay, so again, we don't know what the function is, but we have these 3 different intervals. So when we go to do our trapezoidal approximation, we don't have the same width for each one, so just be aware of that. Alright, so let's go to a trapezoidal approximation. We could even say for this, the integral from 2 to 8 of f of x dx is approximately. That would be one way of saying that. And you could say, of course, trapezoid Riemann sum, but same idea here. Alright, so again, that formula, 1/2 times your width, which for this first one would be 1, times f of 2 plus f of 3. That's your first trapezoid, plus 1/2 times your width here, which is 3, times f of 3, plus f of 6, plus 1/2 times your width here, which is 2, times f of 6, plus f of 8. Answer to it. I get, of course, oh wait, we actually would have to substitute in the values, sorry. We have these actual values, substitute them in. And then you could simplify, but not necessary. Is that what you're going to ask, Mark?
No.
You have different.
How do you get the delta x to 1 and 3 and 2?
So this was the intervals that they gave us. I just simply looked at the numbers they gave us. We didn't know that they were going to be interval lengths, so we had to use the information they gave us. Other questions? Okay. So your homework is worksheet 8. It says to do the work on a separate piece of paper. And again, I recommend that you do some of the problems, simplify it completely to just get that practice. Remember, for first response, you do not have to. If you borrowed some colored pencils, please do return them.